So this is the next QEMU session. I'm not actually a QEMU developer, I work in KVM stuff. So I'll try to do my best to represent the goal of this, but the QEMU guys can chip in and correct me if I say something that's wrong. So the idea here is to talk about why we do QEMU emulation at all, right? So we've seen an example of SVE before, but this came out of a sort of soul searching that the QEMU community has been doing and saying, what is it that they should be doing with their limited resources, given all the random wishes that come along for QEMU. And so there's been sort of a process trying to figure out what are the most important things to work on with QEMU. And Linaro has 3 bright QEMU engineers, so we figured that we should at least figure out what Linaro's members are interested in for us to work on. So we've been talking to sort of in management layers a little bit and trying to get feedback from members at that level. But basically we're going to ask the same questions here and hope that at an engineering level we get a little bit of feedback about how QEMU is actually used. So if you don't have answers ready for us now, we hope that you go back to your member companies and your friends and your colleagues and talk about this and come back to us with wish lists. So brief overview of what QEMU is. So QEMU has 3 main roles. It does system emulation, so that's where you want to emulate a specific hardware platform, the full architecture. You emulate the full system so you can run a foreign kernel in applications. So for example, you could emulate a Raspberry Pi and an x86 server, and that's also what's used as the base for the Android emulator. And today Google actually merges upstream QEMU at regular intervals into the Android emulator codebase. QEMU also does user mode emulation, where you run just a single binary of a foreign architecture on your directly on your system, on your domestic kernel. So one example is you run a native AR64 GCC on your x86 development laptop. And finally, QEMU is also a driver for running KVM VMs, and that's really out of the scope of today's discussion. So we're going to focus on the first 2. So why do QEMU emulation? Well, so one popular use case is for CI purposes, for testing things. Right? So I'm sure the Lava guys can talk about the difficulties of running and managing a board farm. So just running jobs on an x86 server or an ARM64 server using QEMU is an attractive alternative. QEMU can be a very powerful debug environment. You can single-step your kernels without having expensive debugging hardware. You can use fancy introspection and tracing features. You can use stuff like reverse execution. I think Peter wrote an interesting blog post on that a while back. QEMU is popularly used for cross-compilation for targets that aren't good to compile on. It's also used by some companies for system modeling, for actually designing systems. There's just a couple of companies that use QEMU for that purpose. So what's sort of currently out of scope for QEMU emulation is cycle accurate simulation, having some sort of verification that QEMU is compliant with the architecture. It's a best effort approach, really. There's been some talk about trying to make QEMU more modular, but the current thinking, I believe, is that there are better alternatives, alternative ways of doing that. Like System C, for example, and there are GPL challenges for doing that. It's been sometimes asked at Linaro, why don't we emulate this board or that board or this server? And the answer is that that's really hard. That's a lot of work. So we don't try to, say, emulate every single board that's out there. So we try to choose some representative boards that you can use for your main use cases. But that being said, once in a while somebody comes along and says it's useful to emulate this full real system, and there are talks of, for example, emulating a full server system, but currently that's not something that people are working on, as far as I'm aware. And it used to be people were talking about using QEMU for better than native performance, especially if you compare it against tiny embedded targets. That's mostly not really an issue anymore when you can run stuff on a powerful piece of ARM hardware. So some of the potential future work that we do have planned and that we have in scope for Linaro is that we want to try to do a better job of sort of keeping with architecture tips from ARM. So we've already seen with SVE that it was a problem that we weren't really up to date with prerequisite features from earlier versions of the architecture. And when AR64 came along, there was all of a sudden this point where it was very important to get QEMU done very quickly, and well, let's just say that was a challenge. So if you want to support the use cases of running, for example, CI loops for hardware that you don't have yet or that's very hard to come by, well, that whole point is lost if you don't emulate recent architectural features. So that's definitely some of the things that we're trying to do the best we can with the resources we have. There's some example of the stuff that we don't have yet. Right, I'm not going to list all of them, but there's a whole range of RMB 8.1 features, RMB 8.2 features, and RMB 8.3 features that we simply don't do yet. Right, I'm sure some of these will come back and bite us at some point. Right? So for all of you, if you know already by looking at these slides, potentially offline, say, you know, that thing is going to be a problem for us soon already, let us know. Do you want to take this one, Alex, and explain a little bit about your ideas about this one?
Yeah, so there's been some work on the list to improve the use of QEMU for instrumenting your system. So obviously with a dynamic translator, you've got complete control of the system. You can do some potentially do some quite interesting things. So at the moment, we have a simple record-replay supported, so you can boot up a system, record your trace, and then replay it back. And that can be extended to do things like reverse debugging, because obviously you can go back to a previous point in time. But there would be options, for example, one that I'd be quite interested in doing is adding a thread sanitizer, because obviously we can instrument every single load and store, and we can do the same sort of thing as the thread sanitizer on GCC and LVM, and try and detect races in our system emulation. But at the moment, this is all in an embryonic stage, so we're trying to come up with a good, solid API that is going to be flexible enough, but also not expose too much to the internals of how QEMU does things, so other people can develop plugins that will plug into the introspection framework. So if anyone has any particular interest in that, or any questions about that, please shout.
In terms of user mode emulation support, it used to be that was in a pretty bad state, simply because there wasn't a lot of resources to work on it. Linaro has done a lot of work on that, so it's a lot better now than it was a few years back. But there are still things that don't work, like running really complex, large multi-threaded applications like Node.js. We don't see a lot of requests for that continuously, but if that is a case, that causing actual problems for people, we want to hear about it. We also don't support things like VDSO, which would have to be added, and we don't do things like supporting record replay. So there's also stuff that's not necessarily ARM specific that the QEMU project could really need, and we are trying to dedicate some of our resources, some efforts towards some of these goals, and that's just sort of to let people know that that's something we're doing. Right, so there's documentation improvements, not just writing documentation, which is certainly also a needed thing for QEMU, but also having a proper infrastructure for creating documentation. I think some work has been going on, but certainly there's opportunity for more. Another thing we're looking at is if we could somehow support writing device models in some Delta C that makes it easier to write a device model that you can plug into some board and play with. So that's something we're going to try to have some time to explore. Modularization. So right now you pretty much compile QEMU as one big chunk. So having an easier way to say I only want to include these smaller bits. And finally, there's a lot of potential cleanup work to get rid of unused or undocumented code, unmaintained code, and getting rid of outdated documentation. So that's actually all that we had, and that makes sense because we want to hear from you. So I hope anybody has some stories of stuff they wish they could do with QEMU, or that they already do very successfully, and that's very important for them, or any other questions around our QEMU efforts in general.
This is somewhat of a niche use case, but it's one of the things that we often find if we're testing for Cortex-M, and particularly in open source projects where you have to use open source emulation all the way down. But quite often, if if it's a compiler target, it's sort of, you're trying to test something that probably wouldn't normally run on a Cortex-M device. In other words, it's probably got printf, it's probably trying to do some other sort of OS things that are emulated using a semi-hosting. And currently I thought, oh, I'll try and use QEMU for that, and had rather a long slog to try and fight through the single device model, try and get all the memory maps. It was considerably more of a struggle than it was for, say, trying to just get an A-class thing to work. So one potential thing, again, very, very niche, would be great for compiler developers to have kind of, I guess you could, some kind of virtual Cortex-M that has semi-hosting, that you could kind of say, okay, I guess a way good example of this, there's no Cortex-M0 model, there's Cortex-M3. Yes, an M3 will run all the code that you can run on M0, but if for a compiler target, one of the things you want to check is that I haven't snuck in an instruction that doesn't exist on an M0. That's just some suggestions along that line. Again, a lot of work probably for very few people, but...
Yeah. Do you have any comments or thoughts on that?
No.
Hello? Yeah, I mean, you're right that M0 is not something we've done yet. It's one of those things that's, depending on how much feedback we get, that's definitely a useful thing. We could certainly look at doing it. Because mostly it should just be a case of you turn off all the bits that are M3 only. And testing is a bit tricky because checking that you actually don't do something is harder than checking that you do it, if you see what I mean. But yeah, that's something we could do. I do think that some of the kind of the issues you had were because the way that the GCC testing is trying to use user space Linux with an M profile CPU is a bit weird, because it's like all Linux is A profile, but you're saying I want Linux, but I want an M profile, but so it's a bit weird.
Yeah,
but
it's definitely an issue.
it could definitely be easier, though. I certainly think that's true.
All right, I've got one. It's too quiet in here. So we talked recently about enterprise models, right? It's worth bringing up because there's a good group of people here. A lot of the distros today are carrying their own. I'm talking more here about QEMU as the back end for KVM, let's say, but I figure it's relevant. So we have kind of a couple of core models defined in QEMU, and then the distros, there's a RHEL 7- whatever QEMU model for every release of RHEL. It's a little bit different from the standard one. Some of the other distros, whatever the latest Ubuntu is, I don't know, Fantastic Flamingo, I'm not really that up on the Ubuntu releases, but everyone has their own, right? And I think you had said at some point about unifying and then having some kind of effort to go and clean up the enterprise models. So I'm giving you an out to bring up standardizing models if you want to.
Yes.
Vendors.
So I guess this particular issue came up from sort of trying to source the non-KVM use case. But yeah, I mean the issue you bring up is that well, what I've been talking about before is that I feel like it's a shame that we don't do a better job of emulating a really good standards compliant server system in QEMU. It seems to be that there's a lot of people who get platform integration wrong on ARM, and that's a shame for server systems. And it seems like doing that in QEMU could be a good reference platform. It's not.
I agree.
Yeah, that's good to hear. It's a lot of work, right? So I think from the LEC group's point of view, what they've been wanting is to say, okay, let's emulate a full system that has a control processor and all that, so that you can have and that as a base for their CI and development of things like UEFI and other custom firmware.
eChem that works correctly, or whatever it is today, right?
Yes,
Yeah.
but I think certainly also from sort of a general ecosystem point of view that we'll go look at the QEMU model for this and see where how you need to integrate these things. Not that everybody would follow that, or that they should necessarily, but it would be of some value to have a reference platform that works. So I think that could be a very good effort. But we would need a little bit more of people being vocal about it, I think, because it would require a lot of resources.
Does anybody else here care about that, or is it just a small group of us? That's a small group of us. That's it. Okay.
I mean, Christopher's right that it would require a big chunk of somebody working on it. But I think we're kind of gradually going in that direction, because I think when we first started talking about this, you look at the specs and it's like, well, we really need EL3 emulation, we need EL2 emulation, and we need SMMU, we need a GIG-V3. And at that point, I think we didn't, well, we might have one or two of those, we certainly didn't have the whole set. And kind of gradually what's happened is, well, we filled in some of those blanks. So we do have EL3 now, we do have EL2, and we do have the GIG-V3.
An ITS in the right place. And,
yeah, and SMMU patches are on the list. So some of these big lumps of what we didn't have are now appearing. And so the set amount of work you would need to do to put that all together into a complete enterprise platform is getting smaller. So in that sense, well, maybe we want to look at that again and say, well, we've got a lot closer now, so is it worth putting in that last lump of effort to give you something that's actually what you asked for, as it were?
So, are you finished with this?
Yeah.
Okay. Has there been any effort in letting QEMU generate more firmware tables which describe the model in advance? So apart from MacWord does it currently, right? Generate a DT for the model, but is there, so for MacWord we do this, but for other models that if you pick one of the ARM platforms there, then you have to provide a DT, for instance, right, for booting. And wouldn't it be nice if QEMU would, I mean, QEMU knows the hardware and it should be able to do so?
Well, this starts to get us into the religious territory in the sense of, is a DTB really a description of the hardware or not?
Why don't you just describe the model in terms of...
Or ACPI for that matter.
No, why don't you use a DT internally to describe it?
Because the DTB doesn't describe hardware, basically. So the DTB is a description of what the kernel needs to know about the hardware, which is not quite the same thing as what QEMU needs to know about the hardware. Both of those are subsets of what the hardware really is. So the approach QEMU has taken so far is basically we divide everything into two categories. So there's things which represent real hardware, where the idea in QEMU is, if we say this is a model of a versatile express board, then it looks like a versatile express board. And in the same way that if you have a versatile express piece of hardware, it doesn't kind of come with a DTB, a little sort of plastic tag attached to the PCB. You provide it with your kernel, and so you should be able to do the same thing with QEMU. The second category is basically just has the vert board in it, because that is a purely virtual construct, and therefore we know what's in it. We know that all the devices in it, that the kernel is really genuinely going to be backwards compatible with its DTB representation. And so we can say, well, we'll construct a DTB internally that matches with the hardware that we've just created. So you do end up with these two different categories, but there is a conceptual rationale behind why we do the two differently.
But I mean, what you said that normally if you have a real platform, you have the DT, which is true for older platforms, but for newer platforms, not the case. So if you look at what DTs you have for, say, Cavium in the kernel, it's very minimal, and the actual thing is much more mightier DT. And also for midway, I think it's not, that really the DT comes with the hardware. So I think that should be the way, right? I mean, we can't say, yeah, but everyone does it wrong, so we do it wrong as well, or is it?
Well, so I don't really know that much about the midway platform. Well, we have a model of it, but I don't know how close that is to what the real hardware did. So I mean, server hardware is a bit different because the idea is much more that you have UEFI and ACPI and so on.
But you still need to provide some ACPI table information, right, for this?
So for the vert board, we do that.
Yeah.
We generate table fragments.
But if there are anywhere any other hardware that you want to emulate platforms, then it would be a question.
The theoretical idea would be you would run the firmware blob from the hardware on the model. Chances of that working seem quite low,
but that may not be easily available, right? Ideally, the firmware ships, and it doesn't need to be open source necessarily, and especially the ACPI tables come as a blob or something.
Yeah, but we really don't want to get into the business of QEMU models, a thing which is kind of the compound of the hardware and the firmware. That's really weird.
Is that an actual problem? Does it show up as an issue or we don't do it?
No, it was just if just from a general idea, if there's something, then it should provide. I mean, that's yeah. Or just looking at the midway, for instance, that
a lot of this is pretty moot because there aren't really that many 64-bit platforms that support them. Right? Vert is the major one, and then there's a couple of side link boards, and that's it. So Vert is a special case. So there aren't. We don't have a model of the Cavium server hardware because we don't really need one.
I have a question about the fault, the hardware fault in QEMU. QEMU is intended to work as a perfect hardware, and you start and you have Linux, you're happy, but in embedded world, sometimes you have a failing SP flash or tool, and you want to test that your embedded firmware can recover from this error, and there is no happy yet in QEMU to insert failure, and maybe that could be an interesting thing to do.
Yeah, so that's kind of, I guess you call it fault injection, and that's an interesting topic, but it's also quite a big one because at the moment QEMU has no infrastructure for that at all, and so you need some sort of mechanism for defining, well, how do you say what kind of fault you want to inject, and then at the per device level you need to think, well, okay, so this is my I2C controller, what are the plausible faults that it ought to support emulating, and how do you generate those? Do you do them randomly and so on? So I think my take on that kind of thing is that there's only so many huge new features you can add at once, and some of the things that we think are interesting big new features Christoffer talked about in the presentation, and where you have to add a big new global framework for this is how we support this in QEMU, and then you add a bunch of support to individual devices and so on. That's a pretty large chunk of work. So whether it's worth doing that large chunk of work as opposed to some of these large chunks of work is something that's kind of you want feedback from people that's like, this is really critical to us, we really need this. And that would obviously push that up the priority list to try and think about how you would choose to handle that. But you're certainly right that it's the kind of thing that you can do with an emulator that you can't do with the real hardware very easily. So in that sense, it's something that is worth considering. That was my take on a lot of these features, is that you can't say anymore that you want QEMU because it's faster than your hardware, and given that you can get cheaper on dev boards, it's generally not cheaper than your, or not much cheaper than using real hardware. So the question is, what are the things that you can only do because this is a model, because this is an emulator? And so some of the stuff like the tracing and introspection, and also potentially fault injection, these are all things you can't do on real hardware. And so as a project, we should be considering which of these we can do so that we continue to stay relevant, even when we're really quite a lot slower than fast ARM servers and so on. It's like, well, you want people to have positive reasons why are we using this? And the answer is because we can do this and we can't do this any other way.
We have the memtest program, and sometimes you run it and say, this DIM memory is broken, so you should change it. It can be an example for we run broken hardware sometimes.
So interestingly enough, I think last week the kernel team had developed a number of drivers with a lot of fault detection mechanism in there, and they were gonna, how are we ever gonna test this on a longer running basis? And they put together also right up that using QEMU to inject those models on some structured basis would be super useful for that kind of purposes. So that actually also came up. So I think that is probably something we should at least write down on the list of stuff we should start looking at. I think it's good feedback. Anything else?
Would it be possible to support big endian Linux user for IRC support?
In theory, absolutely. If you have a kernel that does this and that demonstrates it working on real hardware, that's probably a good first step. Because certainly that's been a bit of an obstacle to some of our big endian stuff is, well, it's not quite clear how it ought to work, because some of the kernel supporters often seemed a bit sort of rusty and had tended to acquire bugs and not actually having been tested. So it's much easier to say, I know this definitely works because I built this collection of binaries and I checked that they run on the real hardware that's working the way it's supposed to, and then I can check they work the same way on QEMU. If you're doing something on QEMU that's trying to emulate an environment that you don't have, nobody seems to have at all in the real world, then well, A, the question of what you're doing it kind of springs to mind, and B, it's hard to test.
Sure. I've got big endian seems to work on QEMU systems, so it seems like most stuff is there. At least the CPU is there.
Yeah, we improved that quite a bit, I think. And so, if I remember the way this is supposed to work, you should use the same QEMU Linux user. Yeah, I can't remember whether this is half supposed to work or not, but yeah. And so, like ILP32 support in Linux user, which is another thing that people have asked for from time to time, it's, yeah, in theory it could work, and it just needs somebody to find time to do it.
ILP32 was my next question.
Thanks, everybody.